Okay, there's another result here, and I've written it out here. A cross B can also be thought of as the magnitude of A times the magnitude of B times the sine of theta, theta being the angle between the two vectors A and B, times n. And n is just a unit vector that is orthogonal to the plane that A and B are in. In fact, n is orthogonal to the vectors A and B as well. Let's check that this result actually works with our cross product here. We already have the cross product of u and v and the cross product of v and u. We did these on the previous screen. And the magnitude of u, let's figure out what that is. The magnitude of u and the magnitude of v, we'll need both of those. The magnitude of u is the square root of 1 squared plus 2 squared. And the magnitude of v is the square root of 3 squared plus 1 squared. So here I'm going to have the magnitude, sorry, the square root of 5. And here we have the square root of 10. All right, so supposedly, and we already have our cross products, right? We've already determined what our cross products of u with v and v with u are. I'm going to go ahead and do u with v first. Maybe that's the only one I'll do. We'll see. We claim that the cross product of u with v, having computed it directly, is the vector 0, 0, negative 5. And supposedly, that is going to be equal to the magnitude of u, which we determined is the square root of 5, times the square root of the magnitude of v, which is the square root of 10, times the sine of theta, I'll leave that blank for a moment, times the normal vector. So I'm going to write this as a vector here. This is going to be a scalar. And then I'm going to have a vector here. And that vector n is the normal vector that's perpendicular or orthogonal to the plane that these two vectors are in, right? These two vectors, u and v, are in the xy plane. So that means that this vector n has to be lying along the z-axis in the same way that we found these were lying along the z-axis, right? This is the definition of what n is in this context. It's a unit vector, so it has a magnitude of 1, and it's orthogonal to the plane that these two are in. So that means it has no x component, no y component. It has a z component, but when I add the squares of all of those and take the square roots, I have to get 1. The magnitude of this has to be 1. Well, thanks to those zeros, that just means that this is 1. This is our k vector for those of you following along in that context. All right, and now let's go back and look at what this sine of theta is going to be. What is our theta? Well, theta is the angle between u and v. And we have a way of figuring out what that angle is. We learned in the previous section that the cosine of theta was equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. Well, we already know what the magnitude of u and the magnitude of v are. We just computed those. We have the magnitude of u is root 5. We have the magnitude of v is root 10. And the dot product of u and v is the product of the first component in each. That's going to be 1 times 3. Plus the product of the second component in each, which is going to be 2 times 1. Plus the product of the third component, that is just 0. So we end up with the cosine of theta equals 5 over, this is 5 times 2. So if I simplify this, I get 5 root 2 in the denominator. And then I can cancel the 5s. So I get this statement that the cosine of theta is equal to 1 over the square root of 2. Well, from that, I can figure out what theta is. Turns out that's pi over 4. Hope you remember all of this from your trigonometry. So I'm going to stick pi over 4 in for theta. In this particular case, it happens that we get 4 the sine of pi over 4, the same thing as we did for cosine of pi over 4, and that is 1 over root 2, which I'm then going to multiply by, remember how I said that this root 5 times root 10 simplifies to 5 root 2. I'm going to do the same thing here, 5 root 2. So what I have here now, I'll highlight it. This scalar is a result of this arithmetic. Okay, those are equivalent. And I still need to multiply that by the vector 0, 0, 1. Well, these root 2's cancel, and I get that this is equal to 5 times 1 times the vector 0, 0, 1. That is just a scalar on the vector, so that becomes the vector 0, 0, 5. And with the exception of the sign, it looks like this statement is true. So what's wrong with the sign? What's wrong with the sign is that I didn't take the right-hand rule into account. Because I'm crossing u with v, let's draw these very quickly again. U is 1, 2, 0, so it's going to look something like that. Hang on, 1, 2, 0. It's going to look something like this. And v is 3, 1, 0. So that's going to be 3. That's going to look something like this. Those are both in the xy plane. And I'm crossing, because I said I was going to do u cross v first. This is v. I need to do my right-hand rule, u cross v, by sliding my hand along v first. And that's going to turn my hand upside down, and my thumb is going to be pointing down. So the vector that I should have been working with here as my normal vector is 0, 0, negative 1. When I do that, when I make that adjustment, the two sides do in fact equal. As with a lot of things in classes at this level, you get a lot of theory and not necessarily a lot of proof. What I've given you here is a new formula, and I have verified it for one specific case only. Let me draw a line in here because these two things were related but not in sequence. This is not a proof that this works. This is only a proof for this pair of vectors. It's the only thing I've proved is one case. This is an example, however, kind of a confirmation that it works at least for some cases. And the proof of this particular concept, this rule that we've applied here by calling it a formula, is beyond the scope of this class. So we're not going to be doing that proof here. Fortunately or unfortunately, that's just going to be the case with a lot of things in classes like this. But this is the result I wanted you to see for this screen. There's one other sort of vocabulary issue here, and that is, I'll grab a different color of highlighter. Let's go with green. This vector here, you might be wondering why we're calling this unit vector n, and that is because the unit vector that is perpendicular to another vector or to a plane is called the normal vector. And the n, therefore, in the notation here stands for normal. The normal vector is just a vector that is orthogonal, usually to a plane. So that's what that represents. There's one more sort of factoid that I want you to know about this thing we call a cross product. If I take two vectors, and these two vectors happen to be in the xy plane, but they don't have to be. If I take these two vectors and I use them to create a parallelogram, very similar to what we did in the first part of the course, then I can use the cross product. Let's call these u and v. That has been our pattern over the past several sections. Their cross product, u cross v, is a vector. But that vector will have a magnitude. And the magnitude of that cross product vector will be the area of the parallelogram formed by the two vectors. Remember that the two vectors u and v don't have to be in the xy plane. They can be anywhere. They can be floating around in a different orientation. Let's say we have 4 points. I'll call them P, Q, R, and S. And these 4 points have the coordinates -8, 3, and 6, -5, -1, and 3, -6, 0, and 9, and -3, -4, and 6. Well, let's see, I could try and plot those in space. I've got -8 in the x direction, so that's going to be back here somewhere. I've changed the orientation of my attempt at drawing an R3 coordinate system just because I feel like it's a little bit hard to see the way I've been doing it. So I'm going to go back 8 in the x direction, and then out 3 in the y direction, and up 6. So I'll have a point up here somewhere that's P. Q is -5, so it's back a little bit, and then -1 in the y direction, and 3 in the z direction, so it's probably about there. That's Q. R is -6, 0, and 9, so it's -6, 0, and 9 is about there. And S is -3, -4, and 6, so it's here. So as you can see, well, I hope you can see, they're all just kind of floating in space. As it happens, if I connect them, the scale is off here. Let me see if I can scooch this one up just a little bit, make it a little bit more obvious what I'm trying to get at here. There. And maybe this one needs to be moved in a little bit here. There we go. That's a little bit more like it. They're somewhere off the unit planes, right? They're somewhere off the coordinate planes. They're not on the xy plane or the xz plane. They're somewhere in space. But when I connect them, I get a parallelogram. And what I'd like to use this example for is to find the area of that parallelogram. Well, I can take either pairs. I can either take, lost my label for S here. I can either take RS and PQ or QP, or I can take RP and SQ. Let's see, how should I do this? I think what I'm going to do is, I think I'll use the Q, the point Q is kind of my vertex because it's got the smallest values. And I'll use QS and QP. Those line segments, actually I'm going to say that they are vectors, right? I'm going to treat them as vectors. So let's figure out what those vectors are. It turns out the way I have this oriented, I don't need R, so I don't need to worry about this point here, but I could have done it in several different ways. And so to convince us that this is a parallelogram, well, there are a couple different things we could do, but we don't really know the orientation of this. So we'll just take it for granted that this is a parallelogram, and that the vertices that are given, we can choose one vertex to be the common tail, if you will, of two vertices. And we need to figure out what those two vertices are. We'll do that next. The vertex, sorry, figure out what those vectors are. The vector QS, remember this notation, is equal to the endpoint minus the starting point of each of the 2 points that we're working with. So since I'm looking for the vector QS, I'm going to start with the first component of S and subtract the first component of Q. So I'm going to have -3 minus -5, that's -3 plus 5, which is 2. And then I have Q, S minus Q. So then my second component is -4 minus -1. -4 plus 1 is -3. And then I'll have 6 minus 3, which is also 3. So that's the vector QS. And now I will take the vector QP and do the same thing, figure out what the components of that vector are. QP, I'm going to start with the value for the first component of P and subtract the value for the first component of Q, and so on. So P minus Q, that's going to give me P minus Q. So -8 minus -5 is -3. 3 minus -1 is 4. And 6 minus 3 is 3. So now I have two vectors, right? What I started with was 4 points in space. What I've done with the coordinates of those 2 points is I've determined two vectors. And since what I'm looking for is the area of this parallelogram, all I need to do now is find the cross product of these two vectors and find its magnitude. So let's do, well, I'll just write it this way. I was stressing about the notation here, but it's still a vector QS and a vector QP. And I want to find the cross product of those two. So I'll create a little template here. And then I'll put my matrix down here, my I, J, K row. And I've written this as QS crossed with QP. So I'll write that as 2, -3, 3, and -3, 4, 3. Put my brackets on. And I'll use this matrix to determine the coefficients of I, J, and K. When I do this, I actually usually write something like this out. I may not put little lines here, but I'll leave myself some space. And I put my minus sign in here right from the very beginning. I don't want to make the mistake of forgetting that that's supposed to be negative. So I actually write that in right from the very beginning. All right, let's take a look. I'm going to have I times the determinant of these four, this mini matrix, J times the determinant of this mini matrix, and K times the determinant of this mini matrix. So I will have I times -3 times 3 minus 3 times 4, which is 12. Then I'll have J times 2 times 3 minus 3 times -3. And lastly, I'll have K times 2 times 4 minus, where am I? -3 times -3, which is 9. Okay, so that's going to give me -21I. This is 6 plus 9, so that's going to be 15. So I'm going to have -15 J. And 8 minus 9 is -1, so I'll have -1K, or just minus K. And then I can turn that into that other notation, -21, -15, -1. I have the cross product of QS and QP, but what I need is the magnitude of the cross product of QS and QP. So for the last step, I just need to work out what this magnitude is. I'm going to have the square root of -21 squared plus -15 squared plus -1 squared, and this is a job for my calculator, so I'll be right back. That turns out to be the square root of 667. And that does not reduce. 667 turns out to be 23 times 29, but those are both prime numbers. I was hesitating there for a second, but yes, both of those are prime numbers. So 667 does not break down as a square root. The square root of 667 doesn't simplify. So what I have here is that the area of this parallelogram that we found floating in space here, the area of that is 667, square root of 667 square units, which is about 25.8 square units. I'll just stick that in here. That's about 25.8 square units. There is, believe it or not, one more thing we can say about the cross product before we leave this particular video. I know this one's getting long and I apologize for that, but it's all in the same subsection of your textbook, so I want to make sure that it's all in the same video as well. All right, on the next slide, we're going to talk about how to find out if two vectors are parallel. Back when we were talking about the dot product, we said if the dot product of two vectors was equal to 0, remember this is a scalar because the dot product produces a scalar. If that was true, then that meant that A and B were orthogonal to each other, perpendicular to each other. And the symbol we often use for that is kind of like an upside down T. It's supposed to represent two line segments that are perpendicular to each other. It turns out, though, that if the cross product of A and B is 0, this is going to be a vector, the 0 vector. Well, what that means is that A and B are parallel to each other, and a lot like the sort of magnitude symbol, this is two little line segments right next to each other, just one pair though, and that's supposed to indicate a pair of lines or line segments that are parallel to each other. I'm not doing a very good job of making them look parallel. There we go, that looks a little bit better. So those two little line segments are supposed to be parallel. So if we take the cross product of two vectors A and B, and that cross product turns out to be the 0 vector, all the components are 0, then what that tells us about A and B is that they're parallel to each other. Back in dot product, when we were talking about the dot product, if we took the dot product of two vectors and that turned out to be 0, just as the number 0, then that told us that the two vectors were perpendicular or orthogonal to each other. So this is another pretty useful tool. I don't want to take too much time to talk about this, but I do want at least to touch on it. I'll make one point that it should be fairly obvious, I hope, that if you have one vector, say this vector u, and another vector v, I'll use yellow for this one, and those vectors are, to all intents and purposes, on top of each other, then they're parallel in the truest sense of the word, right? I mean, one of them is just a scalar multiple of the other. U is I'll label this other one here, v. U is longer than v, so either somebody took v and stretched it, or somebody took u and shrank it. Right? They're on top of each other in every sense of except that they're not necessarily the same length. If that's the case, then it should be pretty easy to see if you have a vector like, let's say you have u equals 1, 2, 3, and v equals 2, 4, 6, then v can just be written as 2 times 1, 2, 3, which is 2 times u. Down here, I just grabbed a couple of vectors u and v, and it turned out that v was twice as long as u, whereas up here, u was longer than v. This is just a generic example, and this is just some vectors that I grabbed. So yes, the wrong one is longer in this example so these two examples don't really match, I guess is what I'm saying there. But the point I'm trying to make is that if the two vector, if one vector is a scalar of another, it's just been multiplied by a constant, by a scalar, then those two vectors are clearly going to be parallel because they're on top of each other. Well, let's take a look at the cross product of these two vectors. We have I, J, K, 1, 2, 3, and 2, 4, 6. And so my cross product, U crossed with V, is going to equal 12 minus 12 times I minus 6 minus 6 times J plus 4 minus 4 times K. And that is 0 I plus 0 J plus 0 K. That's the zero vector. So if two vectors are on top of each other, they're collinear or coincident, then their cross product will be the zero vector. But what if they're parallel but not on top of each other? Let's just play around with this idea a little bit. The claim is that if the cross product of two vectors is the zero vector, then the vectors in that cross product are parallel to one another. So let's take two vectors. Let's just pick a really nice, easy one like 1, 1, 1. And then let's take a second one, a generic one. I'm going to call it ABC. And I'm going to say that the cross product of those two vectors is 0. If that's true, then I can't write and talk at the same time, apparently. My matrix is going to be like this, and I'm going to take the determinant of that matrix to figure out what the cross product is. That's going to give me I times C minus B minus J times C minus A plus K times B minus A. In order for these two vectors to be parallel, this has to be 0. The result of this, I've run out of room. Again, this is typical for me. The result of this has to be the 0 vector. But to be the 0 vector, each of these components has to be 0. I could write this vector this way. I could say C minus B is the first component, C minus A is the second component, B minus A is the third component, and that must be equal to 0. But these components must all be 0. So that means that C equals B, C equals A, and B equals A. Well, if A equals B, and B equals C, and A equals C, then they're all equal to each other. So for the vector 1, 1, 1, the only vector I can cross with the vector 1, 1, 1 and get a 0 vector is another vector whose components are all the same number. So A, B, and C are all the same, so that means that, let's call this U. If U is 1, 1, 1, then V has to be A, A, A. Or it could be B, 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 or C, 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 because those three things are all the same, but they all have to be the same value. But I can write this vector V as a scalar multiple of 1, 1, 1. So at least for the case of the vector 1, 1, 1, take any other vector and cross it with U, cross with that vector 1, 1, 1. And in order for that cross product to be 0, those two vectors must be coincident. It turns out that the other possibilities, if you take any random vector and cross it with a generic vector, A, B, C, like I've done here with this vector, where am I? This vector here. Crossing it with the vector ABC. Instead of the nice vector 1, 1, 1, say you crossed it with 17, 35, pi or something like that. The result of that cross product will be a system of equations or a matrix that you can solve that has a 0 row. And remember that what a 0 row means is that the system is dependent. The values for A, B, and C, well, the values for at least two of those variables, A and B, for example, will depend on what the value for C is. And so there's either no solution or there is an infinite number of solutions. If the vectors are coincident, as in this case here, then there's an infinite number of solutions. Give me a C and I'll use that C to find an A and B that will work, but C can be an infinite number of values. And so I can come up with an infinite number of vectors. They'll all be scalar multiples of V or scalar multiples of U, but there's an infinite number of them. In the case of no solution, we get a system where it doesn't matter what A, B, and C are. There's no way that these two vectors will ever cross, no matter how much we scale them. And that's what we mean by parallel, right? They never cross. In the context of vectors, coincident vectors are also described as parallel because they have the same direction, or they have exact opposite direction. You might have a vector like this, for example, that has the exact opposite direction from U and V. That is also parallel. I've not done a good job of drawing that so that it looks like it's parallel. There we go. Let's call this vector T. T is also parallel to V and U there, and in fact coincident because it's lying on the same path, as it were. So there are two different ways to be parallel. And you can tell if two vectors are parallel by taking their cross product, and if it's 0, they are either parallel or coincident, which is a type of parallel. If the cross product is not 0, then the two vectors are not parallel.